Here we go. Chapter 8. So yesterday we talked about the cardio system, so the heart system and the blood. So today we're going to talk about the respiratory system and how it regulates things in your body and tries to keep homeostasis for when you are sitting there resting and when you're moving quicker. And then I think the next one's acute exercise responses. So when you're doing, we're just kind of doing the baseline here, and we'll go into more of the details after that. And there's going to be a lot of review here off of anatomy and physiology, more of your physiology stuff here than that. So there's kind of all the things we're going to go over. And since we're going to go over them, we're not going to talk about them here. All right, so there's two main purposes for your respiratory system. Your purpose is to carry the oxygen and remove carbon dioxide from all the body tissues. So those are kind of the two main things. There's a lot of other details that are going on, but that's kind of everything in a nutshell. Is bring in oxygen, kick out carbon dioxide from your body tissues. So there's four ways that we're going to talk about doing that. So there's first is the ventilation. This would be external in. Then the diffusion of that, so you breathe in, then diffusing it from your lungs into your blood, and then the transport of those gases through the blood. We've talked a lot more about that yesterday. And then the diffusion, which is blowing everything out there. Capillary diffusion, more internal stuff there. So here's just the picture of it. Should be all review here. You breathe in through your nasal cavity or your mouth. It goes through the larynx, through the trachea, into the lungs. And then you'll start at the bronchi, and then the tree just gets smaller and smaller and smaller and smaller until you get to the alveoli. And that's where your diffusion is going to take place in those alveoli. Say very fast, pretty much what I just said there. Transport zone, exchange zones. Those are the two things we're going to be going through here. So the lungs are suspended in a thing called the pleural sacs. It's everything inside of your lungs, or inside of your rib cage there. So there's a parietal pleura, which lines the thoracic wall. The visceral is the pleural that attaches, the outside part that attaches to the lungs. And the lungs are actually very flexible. They take whatever shape the rib cage is at that time. So they're made to flex. So your basic anatomy is you have the lung, the pleural sacs, the diaphragm, and the rib cage. So these all determine the in and out of lungs that you have. So as kind of yesterday we talked about, the blood goes from high pressure to low pressure. So as your heart pumps, that raises the pressure, and then that pushes it out to the body. And so it goes wherever the pressure gradient is. Well, the same concept goes for your lungs, is you will have your atmospheric pressure. If I can do a decent job writing here. So the atmospheric pressure is going to make the air, if the atmospheric pressure is greater, then the interpulmonary, in the lungs, pressure is going to flow from the atmosphere to your lungs. So from the atmosphere to the lungs. When the atmospheric pressure is lower, then it's going to go from lungs to atmosphere. And everybody has done that however many times since you've been sitting here and I've been talking, is you're breathing and this is something you don't think about. Well, this can all be described by a thing called Boyle's Law. This is probably going to be a quiz question. Something about what is Boyle's Law. It's basically that when you increase the pressure from the outside to inside, the air is going to flow that way, and vice versa. And so there's this wonderful Boyle's Law, means that the pressure is inversely related, so as one goes up, the other goes down. It's just going to inversely. So inside the container, outside the container, inside the container, outside there. That's as you're breathing. In, out, in, out. So just make sure you got that terminology down there. That would be a really easy, probably even one of those typing questions that I had to grade the other day, or earlier today. So here's what that would look like, how you would measure pressure. Have you guys ever dove down to the bottom of the pool and your ears, everything, you feel the pressure on your ears? Have you ever climbed to the top of a mountain and realized that it's hard to breathe? Again, it's the pressure. So how you measure that pressure, what they're actually saying is, How many times does the gas particles collide? That's what your ears are feeling when it's the water pressure under there. Or when you climb in a mountain, it's how much pressure there is. So if you had 1 liter, here's a little math for you. I probably should do more math in this class, but I don't. 1 liter of container, so let's just say, and you have 20 or 200 milligrams of mercury. So that's just how they measure it. So that's how many gas molecules there are. If you increase the volume, so you go to 2 liters, then you're going to have, the pressure is going to go down. Boyle's law, they're inversely related. Larger area, increase goes down. If you made it smaller and had half a liter, now it would go from 200 milliliters of pressure, and that's how many things are bumping into each other. Smaller area, more pressure. More things bumping into each other. I just love this one. So this is actually the numbers here. So it would be pressure 1 to pressure 2 is going to be the airflow and then whatever resistance is around there. So that's actually at the end. So the pressure coming into the lungs would be pressure 1 to pressure 2 at the very end. And then the resistance down here would be the exchange going on. So that's just kind of a nice graphical way to go kind of with the math of it goes from one pressure to the other and vice versa. So pulmonary inspiration, bringing it in, that is an active process, is what they call it. So it really means it uses ATP in order for it to happen. It involves all the different muscles there. Your diaphragm at the bottom will flatten. Your muscles of your rib cage and everything go up. So those are all the muscles that go on there. It's going to extend the thoracic cavity in 3 dimensions. So forward, backwards, up, down. And so all those things are going to expand in order for your lungs to work. So as your lung volume goes up, Boyle's law says that that the pressure is going to go that direction. And so that's going to change the pressure, going to bring air in. Air rushes in due to that pressure difference. Now the difference is when you're forcing breathing, you're going to use extra muscles in order to make that happen. So even just me sitting here talking, when I make the example of how to breathe, I am using extra muscles to make it so that I can breathe more. And that's what you're going to do during exercise or any of your clients or students, however that's going to work. So the expiration, this is usually a passive process, as in it doesn't take ATP to do it, usually. As your muscles relax, as you're going to tense them all up, and then you relax, that's how the air goes out. You're not actually using any extra ATP in order to make that happen. So lung volume goes down, intrapulmonary pressure goes up, and air is forced out of the lungs. Now, this can be made into an active process, as in using ATP and energy to do so. So that's when you're breathing, so now you're forcing it out as fast as you can so that you can take another breath to continue all the processes that your body needs in order to exercise or to do it when you're tired. One reason, have you guys ever heard of, don't bend over when you're tired, when you're trying to breathe? Why, based on what we just learned here, why would that be the case? Close. If I'm bent over like this, how much can my lungs expand? Not very much. If I'm standing up, I can get more oxygen. I can recover quicker and so that's why you don't let people, when they're tired, bend over on their knees. It feels like you're letting other muscles relax by doing it, but the rest of the body's not going to recover as fast. So that's why your old physical education teacher used to tell you, put your hands up to breathe when you finish something heavy. Oh, when they do those obnoxious, I call them ladders, formerly known as suicides. I just hate that word. When you'd have to run back and forth and back and forth. And when you get done, you want to just fall on the ground and die because you're breathing so hard. And that's keep your head up. So just a random side note there. My tangent of the day. I have another one coming. Let's see, the other parts of today. So there is a respiratory pump. It would just be the muscles that use it. So the intra-abdominals and the intrathoracic pressure. Pressure goes up, compression or squeezing everything out will also then fill. Same concept there. Milking actions from changing pressures assists in the right atrial filling, the respiratory pump. And here's kind of what those would look like. So your diaphragm is going to be compressed, and they actually have all the numbers here too. So if you really want to know the numbers, your atmospheric pressure is 760. And as you're expelling out, you're going to have a decrease. And when you're pulling in, you're going to have an increase. So it's going to have, there is some numbers there that if you really want to know. So diaphragm pulls down, opens up the lungs more. Diaphragm goes in. That's the basics of it. There's a lot of other muscles in there too, but there's just kind of the basics of it.
Objective: to study about human respiratory system, respiration. Respiration involves the following steps. 1. Breathing or ventilation, by which atmospheric air is drawn in and CO2-rich alveolar air is released out. 2. Diffusion of gases, O2 and CO2, across the alveolar membrane. 3. Transport of gases by the blood between the lungs and tissues. 4. Diffusion of gases, O2 and CO2, between the blood and tissues. 5. Utilization of O2 by the cells for catabolic reactions and the production of ATP, CO2 and H2O, cellular respiration. Mechanism of respiration. Breathing or ventilation is the means by which atmospheric air is taken to the respiratory surface for gaseous exchange. The movement of air into and out of the lungs is carried out by creating a pressure gradient between the lungs and the atmospheric air.
All right, so that's pretty much everything in a nutshell. We're going to take a quick standing break. That's pretty much the first 4 chapters that we've gone on in like a nutshell right there. I'm doing what I tell all my gymnasts to do. I tell them when they go to, anytime a gymnast, because they usually are trying to do a handstand and they can't get their shoulders perfectly straight, I tell them every doorway you walk through, you should lean and stretch or lean and stretch to try to get those shoulders, I call it, to open up more.
I do it to stretch the chest. They got to help. You just kind of have to have your arms back there.
Mm-hmm. All right, keeping going. So I have gone through these a couple of times. When I was going through chemo, they always checked on my breath for some reason. Apparently one of the chemos they gave me affected the lungs a lot. And so like before I started, they made a baseline one of these. I actually, instead of being in this guy's just kind of sitting outside here and it's connected to a computer, I actually was in a box that they put me in and it was a little bit too small. But at least it was like clear on all sides. But it was like this little box that like my shoulders didn't fit in, and they had the tube out here for me to breathe into. And they would do all these different measurements. So this would be spirometry. And so like, so here's kind of what they're talking here is you do normal breathing for a while, and that's going to be in yellow here. That's all going to apply to the next slide. So I sit there and just normally breathe. So they would be catching that. And then they would tell me, blow out everything you can. So that would be the expiratory volume. And then I'd sit there and breathe back and forth some more. Then they would test how much can you pull in. So you'd in as hard as you can, as much as you can, and then let it out normally, breathe normally for a little bit. And then the worst one was where they would have you breathe in and then blow everything out. And they'd sit there and like, breathe hard, go, push more, everything you can. And you'd like, feel like you're about to die. They're like, okay, go ahead. Breathe again. So they were actually having me check that entire tidal volume is what they call it, from your maximum to your minimum, or to your minimum there. And there is still even some after that, but you'd never want to worry about that residual volume, because that's the one. The only reason you would have residual volume out of your lungs is because you have a collapsed lung, so you don't want that to happen. But you can never get all the air totally out of your body. They had other ones where they would make me do that aren't on here. I'd be like, was another one. Eventually, though, I think I did it 3 times. So I did it before I started round 1, round 2. And after round 2, they said, your numbers in your spirometry test went down, and so they actually took away one of the chemos, which ended up actually making me go a 4th round of chemo after. So it was just interesting that when I see these things, I'm like, oh man, I have done that like 4 times now over the time. And then like after I was done, like the next major one was like 3 months after, they had me do this again to make sure all my lungs went back to normal. So lots of time, or interesting thing there. So all those terms that you just saw there. So pulmonary ventilation is the air moving in and out normal. Your tidal volume is the amount moved per breath. Your frequency could actually be done by that formula there to give you your frequency. Your alveolar ventilation is how much is in your respiratory zone. And then that dead space is the one that doesn't actually leave. That's the one you never want to actually go out of there. Let's see, some other ones there. Most of the time, like if we did this here in class, I would actually just get one of these kind of handheld things, and you would just put your mouth on it and breathe in and out. My grandma, I remember, and this would have been, I was probably 10 or 11 years old when she was doing this, but she was going through lung cancer, and so they had her breathing into this thing that had like a thing that floated. And as you pulled in, it would pull that part up, and she was supposed to keep it in a certain range as she breathed as much as she could. And so they were trying to expand her lungs. She smoked for her whole life, so she kind of, no offense, deserved it. That's the wrong way to say it, but she did it to herself. Bless her heart, loved her to death. But it was really hard to watch her pass away because she did it to herself. So that's what she used, was something more similar to that. And there's all the things we already just talked about there. And this is a diagnostic tool for all kinds of respiratory diseases. I know I will probably end up doing these things more often because my grandma died of lung cancer and emphysema from smoking. I was around smoking for most of my childhood because of my grandma. My parents never did, but every time I went to grandma's house, so, doctors are a little worried about that secondhand smoke stuff affecting me long term. So I will probably be doing these kinds of tests consistently through when I go get just a physical once a year, I'm probably going to be doing these a lot. And that's just because they're worried about it happening. So after you breathe in, so that was, remember at the beginning there, I said, here's the 4 stages we're going to talk about. Here's where we get to the diffusion part. So this is after you breathe in, it goes through the bronchioles all the way down to the alveoli. So the gas exchange happens between the alveoli and the capillaries where there's blood. Alveoli is where there's air, capillaries are where there's blood. As you inspire, breathe in air, it goes through all the different things, through the trunks, through all those different things. Alveoli are surrounded by capillaries of blood. This is where you're going to either replenish the blood's oxygen supply and remove the carbon dioxide from the blood. So those 2 major functions happen at this very, very small molecular level. Again, should be at least a review at some point. Some numbers here. So at rest, the lungs receive 4 to 6 liters of blood, and that's what we kind of figured out yesterday. There's about 5 liters of blood in a human body. Resting, so the right ventricular output, left ventricular is your cardiac output. So your lung blood flow equals your system blood flow. So that's a little bit from yesterday. Low pressure circulation. So as the lungs go through, there's lower pressure gradients there, and that's very similar. The resistance is much lower due to the thinner vessel walls, which you want because you want stuff to be able to go across from the lungs into the bloodstream. So a very simple way of putting this. Do we got numbers on here that we can read? Nope, not this one. But here's kind of that average one. There's it's 12 here, 8 here as it's going out. So it goes to the lungs, makes that exchange right here. Sorry, it comes in this way and then out this way and then out to the body. And you can see all the different numbers here. There's your blood pressure, 20 to 80. Yeah, that's the basics of it. So the membrane that this is going to go across, this is called the alveolar capillary membrane. So the alveolar wall and the capillary wall are right next to each other. So those should be around all the different blood vessels down there. Surface across which the gas exchange, there's a fairly large surface area of 300 million alveoli in your lungs. That's a lot. I do remember my grandma when she went through her first surgery, they thought that when they cut her open under here, spread her ribs apart, and started by taking a biopsy. And they were trying to figure out what type of, they just had a lump or something on her lungs. And they thought what they were going to do was actually take out probably a fourth of one lung. But when they tested it, they realized it was a more aggressive type of cancer, and they ended up saying it's better for us to leave the rest of your lung. But if it had been a slower growing one and hadn't gone anywhere else, it was whatever stages. The higher the number of stages, the more places that the cancer has gone, and they figured out that it had already gone to one of the lymph nodes as well. So like it's already in the lymph nodes, it's a faster growing cancer, it's not worth taking out a chunk of your lung. But you can think, if you have 300 million alveoli, if you took out a chunk of your lung, you'd be missing that many alveoli, and it would be harder to catch your breath, it'd be harder to move, it would be harder to fight, in her case, whatever was going to happen. So here's how thin thin it is. That's basically move this decimal point over 4 times is where you get that U symbol there. And that's all to maximize the amount of gas exchange you can have as you're breathing. So here's just a picture of what that looks like. These alveoli are these little circular things here, and here is that wall over to the red blood cells. So just to give you an idea, that's a 1 blood cell. So it's actually thinner than the blood cells are. So to be able to make all this go across there. So here is your pressures. Has anybody ever seen one of these temperature pressure gauges before? They're very old concept, and they would actually drop up and down depending on what the pressure is. And then same with this concept is how far this will go. If you have one of these in your house, you can see several of them will drop, and that's when the weather changes to like what we have the last couple of days where it rains. And when the pressure goes back up, these will raise up, and it's probably going to be sunnier and nicer when the pressure is higher. So like that's just what you can see there. So the standard atmospheric pressure, and we'll go over this again another day, is 760 milligrams of mercury, and that's just because that's how they measure it. And it's going to be made up of almost 80% air, 20% nitrogen, a little bit of oxygen, a little bit of carbon dioxide. So that's your atmospheric pressure, and that can all change. And here's all the numbers that can go along this way. Pressure of nitrogen, pressure of oxygen, pressure of CO2 as a part of that 760. So you can add all these together. Little math. Oh, here's my other side rant. This one was planned. The other one wasn't. Has anybody ever been to like Colorado? I've been to Colorado. I hiked the highest peak in Colorado. It's called Long's Peak. And I made it all the way to the top. And I just remember it was just tougher to breathe. And I was just hiking. And I was probably 19 at the time. It was the summer before my senior year. I was like, I should be able to do this, 18, 19. But for some reason, I couldn't figure out why I couldn't breathe as well when I got to the top of the thing. Because they jokingly say the air is thinner, but it's really not truly. Because the percentage of air, tough to see up here, is the same no matter where you're at. But what changes is the pressure around that, because at sea level it's 760. At Denver it's going to be 631. Mexico City is even higher, all the way to Mount Everest. And if you're trying to climb Mount Everest, you need to have a oxygen mask and like carry your own oxygen because it's too thin to breathe. Even though the percentage of oxygen in the air is exactly the same. It's the pressure that makes it difficult to breathe. Also, that's why Denver had a big advantage by having the NBA Finals at their home gym when it's at a much higher level. Makes it harder for who did they play? NBA Finals. Miami. Yeah, exactly. There we go. Miami going to Denver at sea level compared to a mile up, because they call it the Mile High City. Woo! Let's see. Slight advantage for being in Colorado. That's why all of our Olympians train in Colorado. Random side note. Moving on. So we will go into altitude stuff another day. All right, another law that you need to know is Henry's Law. So gas dissolves in liquids in proportion to the partial pressure. Also depends on this whatever kind of medium, fluid medium, the temperature it is. So if it's colder, warmer, that kind of stuff. The solubility in the blood is going to be consistent at a given temperature. So the partial gradient is the most important factor for determining that gas exchange. That's why it's harder to breathe when you're climbing a mountain there. So I got a better picture of this. That was really not a good one. So the atmospheric pressure of oxygen is 159. Your alveolar pressure of oxygen is